Okay, 102 students, let's go through the solutions here together. I need to make a solution guide, plus it'd be good for you to see my thinking. And so I'm going to assign this for the lab. This is going to be in replace of a lab. I think it would be good for you to take the time to kind of hear my thinking, but also self-grade yourself and get any corrections, since this online setting, I can't really write down what your mistakes are and hand it back to you. And so this will be my substitute here. All right, so let's go through this. You might recall me saying that the first four questions will be from each chapter. So these first four from chapter 1 and the next four from chapter 2 and so forth and so on. And so these are the multiple choice here. So of course this first one says I'm very happy that the first question is an easy one to get me started. The subject of this course is of course physics. Yay! So there's the first one. Now, also in Chapter 1 is this unit conversion, and so we've got this 36 meters per second. There's a couple ways of converting units. I like to think of it as maybe multiplying by 1, or sometimes you can just say it's a direct substitution. We know that there are 1,000 meters in 1 kilometer. So if you divide that by a 1,000, that one goes away, and you have a meter, 36. Also, maybe I'll put equals if I'm doing direct substitution. And what this is saying is a meter is equal to a kilometer. 1 kilometer over 1,000. Okay. And then we can do the same thing with a second. We know that an hour would be 60 minutes times 60 seconds in each minute. That's 60 times 60, so that's 3,600 seconds. Or put another way, a second is equal to 1 hour, and we can divide by 3,600. So again, a direct substitution. So in place of seconds, I'll put an hour over 3,600. And maybe I didn't get myself enough room, but there's the original 36 times the 1 kilometer. We've got the 1,000 still on the bottom here. And then over here we've got an hour, and this is a compound fraction, so we would flip and multiply. And grabbing then the calculator, putting all our numbers together, 36 times 3,600 divided by 1,000 would be pretty close to 130 kilometers per hour. So, yay. Number 3, I apologize for the typo. I think this first one, following the pattern of multiples of 10, would have been 43,000 grams. And so this right here should be 4.3, and you'd move it 3 decimals. And so you would have 4,300. And so your best answer is B, but because of the typo, I guess that also makes A an option. So either A or B are fine. And so I'll take either one of those. That was a little bad typo on my part. And then finally, the last one from Chapter 1 here is if there are 8 furlongs in a mile. And so again, more unit conversion, and probably a good one because here we're using something that's not as common. If you're used to the old tracks that you would run 4 times around to make a mile. So if you remember from your high school days, of course now they build tracks that are 400 meters. So 4 lengths is a 1,600 meters. Whereas the older tracks were a little bit longer. They came out to be 1,609 meters because that's 1 mile. Anyways, a furlong is a eighth of a mile, really. See, 8 furlongs make 1 mile. And so the old English system liked to do divisibles of 2. So you had a mile, then you had a half a mile, then you had a quarter of a mile, then you had an eighth of a mile. And then they would start giving it names, and furlong is just that. So whether you know what it is or not, in fact, I think the main point of this problem was to show you don't know it, but you can still do a unit conversion. It says how many furlongs does a horse run in a 4-mile race? And so horse races are still labeled in furlongs. We don't see that word much too often, although we do see it in an acre. So maybe I should mention an acre here in a second. But obviously, then we have something like this, 4 miles. And of course, we also have 1 mile equals 28 furlongs. So if we do a direct substitution, a mile is equal then to 8 furlongs. Okay, and so treat your units, like back here, treat your units just like you would do a number. So here in place of meter, I put what it's equal to. Just like in place of a second, I put what it's equal to. So here, I put what's equal to a mile. It's 8 furlongs, which makes 32 furlongs. So this would be answer A. And in case you're wondering, an acre then is a plot of land that is 1 furlong long. And another way, instead of dividing things by 10, sometimes they'll divide them, by half, they'll actually divide it by 10, which we are more useful in the metric system. And so if you take a furlong and divide that by 10, you get what's called a chain. Now, again, not a very popular word, but a chain is a tenth of a furlong. Okay. So if you take a mile, 5,280 feet, and you divide it by 8, you get a plot of land that is 660 feet by a chain, which divided by 10 is 66 feet. And so the chains were nice because literally they would make chains that are 66 feet. They'd be literal chains. And so as they would make plots of land, they would, connect them together and pull them tight and say, okay, this is your plot of land. And they'd be made out of a hard chain that would keep it same length so that they can measure things accurately. Anyway, so if you connected 10 chains together, you would get a furlong. And then, of course, did that 8 times, you'd get a mile. But that's why we've got this weird number, this 660 feet by 66 feet, coming out to be 43,560 square feet is what an acre is. And so there's another weird units, but acres are still often used. So I would say acres are still common, even though the units that are used to measure the acre are not. Okay, so that being said, that's the first 4 and maybe a little side information about an acre here. Let's move on to the next 4. The next 4 should be out of chapter 2 where we get into motion. It says an object is accelerating when its speed or direction changes. Yeah, so the definition of acceleration is when a change in velocity, and a velocity has speed and direction. So if either one changes. So here, if it's only direction, no. Only when it's speed, no. So it would be 5 would be A. Here it says a child is traveling at 5 meters per second on a sled, passes by her younger brother. If the average acceleration on the sledding hill is 2 meters per second squared, How fast is she traveling when she passes her older brother 4 seconds later? So the conceptual meaning of 2 meters per second each second means you gain 2 meters per second every second. So 4 seconds later. So you would gain 2 every second. So you'd gain 2 and then 2 more and then 2 more and then 2 more. So that's a total of 8 you should be gaining. And it's a change, it's a gain. And so on top of the 5, 8 and 5 make 13. So I guess you could also calculate this by doing the change in speed is acceleration times time. And then change in speed would be final minus initial. Then you can get final speed by putting in initial of 5, an acceleration of 2, and a time of 4, and get your 13 if you want to actually plug in the numbers. But I think this one was not really designed to be plugging in the numbers, but to understand the conceptual meaning of what do you mean by 2 meters per second each second. So you gain by 2, 2, 4, 6, 8. So we're going to gain 8. We're already going 5. We're going to gain 8 more. Okay, so if the mass of an object of a freely falling and double its acceleration is, and hopefully what you got out of this chapter, and then very important by Galileo, is that freely falling objects have the same acceleration. Big object, small object, without including air friction. So D would be the right answer there. Now, later on, we talk about this again, and I believe that this would be chapter 3. But if you were to double its mass, that means you would double the force pulling it down, doubling its weight, but you would also be doubling its mass. And so the force and the inertia each get doubled, giving you the same acceleration. And so that's our argument going into the next chapter. When we go from describing motion to explaining motion, we see why the objects have the same acceleration. But that's a little early for this question. But the question itself is just our first experiment that you drop Bob or you drop anything and it has the same acceleration if you do not include anything else but gravity. All right, so the last one from our speed, velocity, acceleration, our chapter 2, you throw a ball straight up at 30 meters per second. How many seconds elapsed before it is traveling down at 10? And so the value of G is roughly 10 meters per second each second. So going back to the meaning of acceleration, that means it changes by 10 every second. And so on the process of going up, then acceleration would be down. It would change by 10, but it would be a decrease. So after 1 second, we would have gone from 30 down to 10. After the next second, we would go down to 10. So we would go from the 20 to the 10. After the next second, we would go from 10 to 0. We'd come to a stop. So it would take 3 seconds before it came to a stop. Then it would start to move downward. And in this case, it's moving down, and the acceleration is down. So that means it speeds up. So it would go from 0 up to 10. So we're looking at 4 seconds. And so the answer should be 8, should be D. And of course, you could also do this mathematically using that same formula, final speed minus initial speed equals acceleration times time. Our initial speed is 30. Our final speed, though, is a minus 10 if you're going to then do this mathematically because it's going to be going down. So final speed is minus 10 minus initial speed, which is plus 30, acceleration of 10, and then t. And so this is and the acceleration is down, so negative. So that'd be a negative 40 divided by negative 10 and give you a time of 4. So again, you could do it mathematically, but I really don't think that was the intent of the author for this problem. Good problem. Okay, so now going from describing motion to explaining the motion. So here's chapter 3. A ball with a weight of 20 newtons is thrown vertically upward. What is the acceleration of the ball just as it reaches the top of its path? And this really kind of ties back into describing motion, because without explaining the motion, we just said the acceleration is always 9.8 or roughly 10 meters per second squared in a downward direction. And it doesn't matter whether the ball's going up, it doesn't matter if the ball's going down, it doesn't even matter if the ball's at the top. Remember, at the top it has zero speed, and so there is a temptation for students to say it has zero acceleration, but that's just a confusion between acceleration and speed. So hopefully you don't do that. Do not confuse the two. Easy to do, but at the very top, so it goes up and then down. So it's going from a positive speed to a negative speed. If I was doing a graph, I would say, here's the speed, here's time. It's going from a positive speed to a negative speed. And right there at the top, it has a speed of 0. But it does have a change. It does have a slope to it. And that slope is the same, regardless of whether your speed is upward, your speed is downward, or your speed is at the top, which is 0. Anyways, so I don't think we have the option. Let's tell the next page. Here they are. And so we should have 10 meters per second upward, no, downward, yes. So here's the 10 downward. So 9 should be a C. All right, a parachute reaches terminal speed. Okay, so this is again kind of that free body diagram. But if you're reaching your terminal speed, that's a fun way of saying your acceleration is 0, which according to Newton's second law would mean your net force is 0. So what's pulling you down is your weight, and air friction is pushing you up, and it must then be equal to your weight in order for your net force to come out to be 0. So for a human skydiver, I understand that's about 120 miles an hour. Of course, it depends on what kind of shape your body is making, because humans can change their shape. But in a general, arms out, free fall position, it's about 120 miles per hour. So you got to get up to enough speed before that air resistance equals enough to equal your weight. If you ever held your hand out a car window, especially on a freeway, you'll feel how much force that is. Now, that's still not enough to equal your weight, because on the freeway maybe you're going 65, 70, maybe even 80 miles an hour, but you're still not going quite 120. And of course, it's not your full body. But anyways, a parachute reaches its terminal speed when her weight is 0. No. When the force of air resistance exceeds her weight. No, if it was more than that, that would be a net force up and she'd be slowing down. Okay, if the force of air resistance is equal to her mass, no, not her mass, her weight. If the force of the air resistance is equal to her weight. All right, finally. All right, so 10 would be D. All right, looks like we've got 2 more here on explaining motion. A ball with a weight of 40 newtons is freely falling towards the surface on the moon. What force does the ball exert on the moon? Well, this is a Newton's third law. Remember, if object 1 puts a force on object 2, then 2 puts a force on 1, equal and opposite. So the ball has a weight of 40 newtons. That's basically saying that the moon is putting a force of 40 newtons on the object. So according to Newton's third law, the object should put a force of 40 also. Equal in magnitude, opposite in direction. So if it's pulling it downward, then the ball would be pulling the moon upward. And so 11 should be C. All right, and then finally, a child standing on a bathroom scale while riding in an elevator. The child's weight, let me just pause right here. These are always a hard one, because if this is a scale, we need to remember that the way scales are designed is they read this upward force. So they don't read net force. They don't even read weight. But if done right, the upward force is equal to the weight. And so if you're not jumping on a scale or moving on when you're on the scale, if you're just standing still, then the upward force does equal your weight, and then the scale operates as intended. But I'll say it again, a scale does not directly read weight. It reads an upward force. So if you're in an elevator, the child's weight when the elevator is not moving is 50. All right. So if you take it when the child's not moving, you know that the acceleration is 0, which means the net force is 0, which means the force down, which is the weight, equals the force up. And so maybe I'll say force up minus weight has to come out to be 0. And so force up is equal to the weight. So that's the way you're supposed to use a bathroom scale. You're not supposed to put it in an elevator. You're not supposed to jump on it. You're supposed to be stationary, so your acceleration is 0. You're not supposed to be leaning on anything else so that there's other forces involved. There's just these two forces, the weight of the scale pushing up on you or the force of the scale pushing up on you and your weight, and those two should come out to be 0. But if you put yourself on an elevator that was accelerating, or in a car or a truck that was accelerating, then no longer does this upward force equal the weight. Or if you had other forces, you were leaning on a table or something, it doesn't equal your weight. So it's only when the scale is done right. There's only these two forces, no acceleration. All right, so what they're saying in here is the child's weight when the elevator is not moving is 500. Okay. What does the scale read as the elevator it comes to a stop at the 10th floor on its upward trip? Okay, so it's important to know which way we're moving. We're moving upward, so I'll put a little V, we're moving upward. And we're coming to a stop. And so that means your acceleration is opposite to the direction you are, which is also the direction of the net force. So you want the net force to come out to be a negative number. And back to here. I put 0 because this was when they were stationary, but now I want the upward force minus the weight to be less than 0. And so that means the upward force needs to be less than the weight. All right, and so less than the weight is A. All right, good. Let's go on to the next chapter. So this would be chapter 4, and we get into our circular motion. 13, it says, in uniform circular motion. Let's see, maybe I should draw a picture over here. But up until this point, we've had things going in only one dimension. Maybe I'll say up. And so we talked about in the last problem how if it has an acceleration or a net force down, that would slow it down. And in a problem a little bit further ago, we talked about and mentioned that if the net force was upward, it would go faster. So when the net force / acceleration is in the direction of the velocity, they go faster. But when the net force acceleration is opposite, they go slower. And when it's perpendicular, it turns it. And that's what happens in circular motion, uniform circular motion. Because uniform circular motion means we go in a circle, but we go at the same speed. And so we must be having an acceleration or a force that is perpendicular to the direction. So in uniform circular motion, the acceleration is vertical and the velocity is horizontal. Well, only at one moment in the circle. So if I drew a whole circle like this, the acceleration is vertical. So down at the bottom, the acceleration would be towards the center of the circle, true, while the velocity is horizontal. So that's true at a point on the circle, but I don't think that's the best answer here. I think that only happens one point on the circle. So let me keep reading. Acceleration is perpendicular to velocity. Oh, absolutely. That's really kind of the crutch of the learning, is to say that, look, when you have an acceleration that's perpendicular to velocity, it doesn't make it go faster, it doesn't make it go slower, it just makes it turn. So I'm pretty sure they want B here for number 13. Acceleration is parallel or anti-parallel to the velocity. No, parallel would make it go faster, anti-parallel would make it go slower, wouldn't be uniform. Wouldn't be turning either. Acceleration is vertical while the velocity is any direction. No, those are all, that's a dumb one there. Okay, so I'm going to go B. So 13 wanted B. All right, an airplane flying south at 40 meters per second. What is the magnitude of the airplane's change in velocity if it is later going west? All right, well, if we made kind of a grid here, in a compass rose, we usually put east on the positive x-axis and west on the negative x-axis. I don't think we'll need the north and south, but those go on the y-axis. So here's our compass rose. It says an airplane is, oh no, south, and then west. Oh, we do need a south. Okay, my bad. An airplane is flying south. So we have this original 40. And then what is the magnitude of the plane's change in velocity if later it is going west at 30? Now, this one's a little harder than I first gave it credit. I thought it was a one-dimensional one, but it actually is 2 dimensions. Let me write here that change in velocity is final minus initial. If we put little arrowheads over them and move initial to the other side, I think it looks a little cleaner this way. But this is saying if you took the initial, so an airplane flying south, and you drew another arrowhead representing the change, those two together would equal the final, which is that way. So this right here would be the change. So the change is represented from with an arrowhead that goes from the end of the first one and then goes until it is terminating on the end of the final one. So this right here would be a visual representation of the change in the velocity. And they gave me one of the perfect triangles, a 3, 4, 5 right triangle. So using Pythagorean's theorem, 30 squared, which is 900, and 40 squared, which is 1600, and adding together I get 2500. Squaring that, I get 50. So the magnitude would be 50. They don't really ask for the direction. It's not quite northwest, but it's close to northwest. Northwest is really 45 degrees. Those of you who know a little trigonometry know that this 3, 4, 5 right triangle is actually 37 degrees. And so drawing it back here, it would be 37 degrees west of north. And so it's pretty close to northwest. But we don't need that one. We just need the magnitude. So it would be D. It's 50. And that's just Pythagorean's theorem. Otherwise, you would need some trigonometry, which this class is not geared for. All right, next one. By what factor does the centripetal acceleration change if a car goes around a corner at twice the speed? And this is more of a mathematical question. It's saying what would happen if you doubled the speed. So maybe I shouldn't put equals. But if I were to double the speed, so if I were to go from v to 2v, remember the whole thing's got to be squared. So this would be 2 squared, v squared over r. The 2 squared makes a 4. And the v squared over r is what you were getting before. So this would be 4 times what you had before you picked up your speed. So it would increase by a factor of 4. So 15 would be B. Which of the following statements about projectile motion is true? The force on a projectile is constant through flights. That's true. It's constant and down. So maybe we should keep reading here. The acceleration on the projectile is constant throughout the flight. So force, acceleration. Yeah, those are both true. Oh, it's going to be with this all above, huh? Okay. Horizontal and vertical motions are independent. Yep. And so it's all of the above. Yep. That was our projectile motion. Oh, I guess we changed chapters, 12, 13, 14, 15. Okay, so now we're on to our projectile here. Okay. Two spacecrafts in outer space attract each other. I lost count here. So which chapter are we in? 1 through 4, 1, and then 2, and then 3, and then 4. Okay. So we just finished up 4 on our projectile stuff. And motion in space, I guess, is what we showed, because we had projectiles and we had circular. Okay. So then we get into chapter 5. All right. So here's chapter 5, where we would begin to do a universal law of gravity. And so two spacecrafts in outer space attract each other with a force of 20 newtons. What would be the attractional force if they were half as far apart? So what you're saying here is, if you have that, so a certain mass and a certain distance, and then you take that distance and you cut it in half. And so this is a lot like we did up here with the centripetal. We would have G, M1, M2, and we would have to square both of these. So this would be an R squared over a 2 squared. And that we can flip and multiply, because that's what we originally had, which is the 20. And so what you're really saying is it would be 20 times 4, which is 80. And so 17 should be D. 18 says the gravitational constant G in the law of universal gravitation is believed to have the same value throughout space. Yes, that's why we call it a universal constant. That was the beauty of Newton's law of gravity. It kind of put all these ideas of gravity, whether it be gravity from the moon or gravity wherever, from the sun, from the moon, from the earth, but they were all the same. And so hence the name universal. And Newton was the first one to do that. It leads to the determination of the mass of the Earth. Sure does. It is believed to be constant with time. It sure does. And so I guess we're going with all of the above here, D. Also in here was the discussion about tides. And so remember that if you had the planet Earth, here's the rock, and here is some object, whether it be the sun or the moon or harder, some combination of both of them. There would be a bulge of the water, because the water can flow and is affected by the force a little bit more on this side. But also, and this one's a little bit harder to understand, but there would be a bulge of water on this side of the Earth. Not because the water is pushed away, but because the Earth itself is pulled in more than the water. So everything is pulled towards the sun or the moon, and this end is pulled the most. The Earth, its center, if you will, is pulled medium, and this is pulled the least. And so it gives it a kind of elongated effect. And the Earth, of course, is rotating underneath it. So if you kind of imagine yourself on the Earth riding around in a 24-hour period, you would move into this bulge, it would be a high tide, and then out of the bulge. And since the water had to come from somewhere, this would be low tide, and then high tide again. So you'd have 2 high tides and 2 low tides. So 2 high tides and 2 low tides in a given day. So 19 should be B. All right, Mercury has a radius of about 38% of the Earth's radius. and it has a mass of only about 5.5%. Estimate the acceleration due to gravity. Well, this could be a pretty hard one. We know that acceleration is force over mass. And if we then say the force is the two objects, let's say I'm holding a baseball, and so it would be the Earth and the baseball divided by their separation, and then divided by the mass of the baseball. Let's call that number 2. The mass of the baseball would go away, and you would just have then the mass of the Earth, the gravitational constant, and the distance away, which would be roughly the radius of whatever planet you're on. And so this is the little formula to get the acceleration for whatever planet you're on. Now, we know that when you're on planet Earth, it's 9.8 or roughly 10. And that's where it can be helpful, because if you take the mass of Mercury, which they say is 0.055 the mass of the Earth, and you take the radius, which they say is 38% of the radius of Earth, and you square it, you're going to get something that looks like this. Let me put it up here. Now you're going to get G, and let me put the mass of the Earth first, and let me put the radius of the Earth squared, and then if I put my numbers, it's 0.055 and 0.38 squared. And this right here would be a discussion about Earth. And so this would be roughly the 10. And so definitely a hard problem. And now that I look at it, I'm kind of wondering if this would be the hardest one on this test here. Because we've got the math and the numbers, which has that square in it, but we also have to go back to the Earth. So let's see what we get. I'll just do this number, 0.055, and then divide by 0.38 squared. So all that together is about 0.38. And then times the 10 makes about a 3.8. Looks like about a 3.81. And so looking like D here is going to be the matching number. All right, that was a tough one. And I think that's the end of chapter 5. Okay, good. And then the last 4 here, chapter 6, are about momentum, I'm sure. So how fast would an 80-kilogram person need to be running to have the same momentum as an 18-wheeler, which is 24,000 kilograms, rolling along at 1 mile per hour? Now, maybe an added twist here is they gave us some units that we don't normally work with. We don't normally work with meters per second, and nor do we usually match them with kilograms. That's a metric system, and that's an English system. But in this case, we can, and maybe we'll leave it that way, because they want you to say, you know, the mass of the person times the velocity of the person must be the same as the mass of the 18-wheeler. I'll put W times the velocity of the wheeler. So this is the 24,000 in units of kilograms. And then this is a speed of 1 mile per hour. So keeping those same units, for the person, we can put in the 80 kilograms, velocity of person, and this comes out to be 24,000, and then we would have kilogram miles per hour. And so the kilograms would cancel, and we would be left with speeds in these mixed units, which is good. So no point in making this hard and trying to mess with the units. That actually is part of chapter 1. So you could say that this turned out to be a hard one because it wasn't just about momentum, it was also about chapter 1. Now, if I divide by 80, I can get rid of a 0 on each side, and 8 goes into 24 3 times, so that looks like 300. And so 21 would be D. 22 looks like it's another momentum one. It says, why is skiing into a wall of deep powder less hazardous to your health than skiing into a wall of bricks? Well, one thing we hopefully got out of this was that the force to stop something was the change in momentum divided by the time taken. And anything that would either reduce your change in momentum, in other words, not coming to a full stop, would mean less force. So maybe you only slowed down to half your speed. Or maybe you had less mass, be less force. Or something that increased the time it took to slow down. So when we compare these two examples, it's you that are skiing, and I would assume that they're implying here that it's the same person, so it's the same mass, the same velocity, and the only difference is what you're colliding into. But the contact time would be different, and for that matter, the contact distance, so that a softer object, you would squeeze it in more. There'd be more contact time, which, like I said, is also distance. But it's not really about distance as it is the time. And so the increased stopping time in the powder is a smaller stopping force. Yeah, I really like that of all the options. It's not a decreased stopping time. The change in momentum is less. I don't think so. They're implying that same person, same speed. So, and the impulse is less. The impulse is the change in momentum. So C and D are saying the same thing. So A is the best option here. And then 23, it says a coach is hitting pop flies to the outfielder. If the baseball, which has a mass of 145 grams, stays in contact with the bat for 0.04 seconds and leaves the bat with a speed of 50 meters per second, what is the average force? So taking this same formula and calculating it, we could say that the change in momentum would be mv final minus mv initial over contact time. They gave me the mass, 0.45 if I do it in kilograms, and since they're going to ask for a force in newtons, and a newton has a kilogram buried inside it, I'm going to need to change that. So again, this can be a little hard one because we got to do a unit conversion. The final speed is 50 meters per second. The initial speed is 0, and the contact time is 0.04 seconds. And you can see the kilogram meters per second squared, so they're all going to be newtons, although that's all you have here for an option. So that's not a surprise there. But it's the 0.145, so that's important. And then times the 50 and divided by the 0.04 gives me about 181. So it would be D. All right, and then finally the last one here on the multiple choice, and then we'll go to the free response. It says that Carmen is standing on a giant skateboard, which is initially at rest. So I'm going to take that to also mean that it's not just Carmen, but it's also the skateboard. Or, well, they say the skateboard's initially at rest, but then so is Carmen. So if I use conservation of momentum here, and I look at my two objects, my initial momentum is 0, and maybe to make it clear, I'll say it's a 0 plus a 0. It's the two objects added together, and they each are not moving. They each have 0 momentum. So if we ignore frictional effect from the floor, okay, what is the momentum of the skateboard if Carmen walks to the right? So when I add up my two momentum, Carmen is going to have a plus 500. And these are the units for momentum, kilogram meter per second. Okay, and then of course plus the momentum of, let's see, wait. What is the momentum of the skateboard? Okay, so this would be S, skateboard. anyways, it's got to go the other direction. So if Carmen goes this way, skateboard goes that way, and then the skateboard must have a momentum of negative 500. Okay, or maybe we'll just say left here. So this would be to the left, 500 kilogram meters per second to the left. And it has direction, so we'll rule out C, and then B and A wouldn't count either. All right, so hopefully that went well for you. Those are the 6 chapters, and that's the multiple choice then. Let me move into then the free response. Okay, so the free response, here were your 10 questions. Maybe I'll just get myself a pad of paper here and say, all right, number 25. So number 25, and maybe I'll do it together with 26 because there's 2 from each chapter, starting in chapter 2, and they pretty much match. And so maybe to help your understanding, I'll kind of merge them together here. But it says here a softball is released from the top of a very tall building, neglecting the air friction. How far does it fall in 2.5 seconds? Well, one formula we had was distance equals 1/2 AT squared. The bad thing about that formula is it was only valid if your initial speed is 0. Which, for this problem, it is 0, because it says starts from rest. So that's good. But if you tried to carry that down to number 26, you'll get yourself into trouble, because 26 says a bird flying with a speed of 8 slows to a speed of 4. So we wouldn't want to use that for 26. We'd probably want to use the more general formula, average speed times time is distance. And for that matter, we could do that up in 25. And so 25, we have some options. We could do the general one, or we can do the specific one. I'll do both here. And so for the softball, we have an acceleration of 10 meters per second squared. And for 2.5 seconds, and we square it. And I'll start with the units. If you square both of these, you get seconds squared, which cancels with that second squared, and you're left with just the units of meters. If you get out your calculator and go 1/2 times 10 times 2.5 squared, you get 31.25 meters. Now, this one is a little bit maybe harder here because you got to get that average speed. And that average speed would be something like this. What do you start at? 0. And then what do you finish? Add that. Divide by 2. That would be your average speed. Okay, so in this case, 2.5 seconds, let's see, after 1 second, it's going 10. After 2 seconds, it's going 20. And half of that would be 25. So this would be 25 meters per second. And for 2.5 seconds. So if we take this 25 and divide by 2, and we multiply by 2.5, we again get 31.25 seconds. Meters. And so this would be the same. So either option, but I have a feeling that when I start to grade them, I think I'm going to see most of you do it this way. Hopefully I won't see it here, but let's then do number 26, because here the bird starts off with a speed of 8 meters per second, slows down to 4. And so that's going to be the average speed, the beginning and the end divided by 2. And let's see, how long did it take? Bird did this in yeah, in 4 to 4 in a time of 5 seconds. 5 seconds. Okay. So the time is 5 seconds. So again, looking at the units, seconds would cancel off, and we're left with meters. So the bird's average speed, that'd be 12 divided by 2 is 6. 6 times 5 is 30. So we're looking at 30 meters per second. All right, well, let's move on to number 27. And for that matter, might as well put in here number 28. Because, again, these are from chapter 3. And they pretty much go together. They're explaining the, they're explaining motion, where these two were describing motion. All right, so let's explain it. It says, when a force of 550 newtons is applied to a 35 kilogram block on a flat floor, it slides across the floor with a constant speed. Now, let me pause right there. We know acceleration is net force over mass. And this first sentence is saying constant speed. That is a clue to say the acceleration is 0. And you are applying a 550 Newton force. There would be some friction, and we would be dividing it by the 35 kilograms. And what that would say then is this would give us the idea that our frictional force is 550 newtons. And so that's what the first sentence actually gives us. Now, we don't know that we need that till we actually go on to the question, which says, how much force must be applied to have applied to the box to have it accelerate at 1.5 meters per second each second, which of course makes sense. You're thinking, well, it's got to be more, right? I mean, it took this much just to overcome the friction, so it's got to be more than that. Yeah, okay, I would agree it's got to be more than that. And then how much more than that? So let's go back and kind of do the same logic. Acceleration is the net force over the mass. This time the acceleration is 1.5 meters per second, not 0. And it would be whatever force you're applying minus the friction. Minus the friction. That's why we needed this. All right, so we're going to need that number over the mass. All right, so 1.5 meters per second squared equals, and so there's we're after what force. The friction is 550 newtons, and the mass is the 35 kilograms. So bringing this to the other side, which would be 1.5 times 35, equals the 52.5, equals the net force. By the way, I have a feeling that many people might have just stopped right here. What you did is say net force equals mass times acceleration. And you took the acceleration, you took the mass, you multiply them together, and you got the net force. And that's half right. I mean, mass times acceleration does equal net force. It does not equal the force you have to apply. It does not equal the frictional force. It equals the net force. And so there's 3 different forces that this problem could have asked about. And if it had asked just the net force, then just mass times acceleration, which would give us this 52.5 newtons, we would be done. Hopefully, if you got the 52.5, you paused and said, well, wait a minute, it's got to be more than the 550. I mean, it took 550 just to keep it going at a constant speed. Anything less than that, it's going to slow down and stop. To get it to accelerate, you got to be over 550. And sure enough, you do. You got to add that. So in other words, this is 52.5 above the 550, right? You need the 550 just to match the friction, and then you need this much more the 52.5 to overcome that. And so I guess that would make what? 602.5 newtons. So there is number 27. And you'll see 28 is a lot like that, right? See, 28 says that you have a 4.5 kilogram relief package that's accelerating at 3.25 meters per second as it dropped from the helicopter to the stranded victims in the canyon below. All right, so here's the package. Maybe it has a little parachute on it, or maybe what they would just call a drag sheet. They just tie a big long string to it to make some friction, and so you've got gravity pulling it down, its weight. And remember, if that was the only thing, it would have an acceleration of 9.8. But it's not the only thing. There is some frictional. Okay. And hopefully you didn't forget that, but hopefully it's pretty clear, because if there was no friction, we would not be talking about an acceleration of 3.25. We would have an acceleration of 9.8. Oh, likewise, the question just says, what is the frictional force? So you know there's got to be a frictional force here. Okay? So that's what we're asked to find. Now, again, be careful with this one, because, again, just like this 27, it might be tempted to just say, okay, net force is mass times acceleration. And although that's true, that's not what the question is asking. The question is asking for the frictional force. If it was only asking for the net force, then you could just take its mass of 4.5 meters per second squared and multiply by its acceleration of 3.25 meters per second squared and get 4.5 times 3.225 and get 14.6 newtons. And I'll say it again, if that's all they were asking for, net force, we could stop here. But remember, they could be asking for net force, or they could be asking for the force pulling it down, which in this case would be weight, or they could be asking for the frictional force. Now they ask for the frictional force, which I think is maybe the harder one to ask for, because weight we know as mg. So if they're asking for weight, that would be pretty easy too. That would just be the 4.5 kilograms. And if we just want to call it 10 for simplicity, we would get 45 newtons. So that's what I would have done if they asked for the weight. This is what I would have done if they asked for the net force. Of course, what they asked for was the frictional force. So now I need to do really back to here, although I already did this much of it. So I'll just say then that net force is the weight pulling it down minus the friction. So the net force is the 14.6. The weight is the 45, and then minus the friction. So I'll put friction over here and get 45 minus the 14.6. So 45 minus 14.6 is 30.4 newtons. So remember, these got really two parts to them. This has got a first part here to get the frictional force. This is really the same thing, but instead of the frictional force, I give you the pushing force. See, this one I gave you the pushing force. This one I didn't directly give you the pushing force, but I gave you the mass so you can get the pushing force, and you can find the friction. All right. So, again, hopefully those went well for you. Parts of them are a little tough. Hopefully you worked out the solution so I can see your thinking and give you lots of partial credit if you didn't do it completely all right. Okay, let's move on here to... Actually, it looks like these next three are the next chapter. Yeah, there's only one on chapter 5. So these next three are from chapter, let's see, 2, 3, must be 4. Because here's 2 on projectile motion. Really, these are kind of one and the same. And here's a turning one. So here's a projectile. So let's try number 29. And as you'll see, it goes hand in hand with number 30. Okay, so number 29 says that a golf ball is hit with a horizontal speed of 35 meters per second and an upward speed of 15. What is the horizontal speed and the vertical speed 2 seconds later? All right, so hopefully we learned that the acceleration, and I'll put a little h for horizontal, is 0. There is no change in speed. So we could just simply write that, hey, it had a speed of 35 meters per second. I don't think there's any point in making a chart, but if that was at time 0, 1 second later, it would still have a horizontal speed of 35. And 2 seconds later, it would still have a speed of 35. And that's what we're after, 2 seconds later. Now, the acceleration in the vertical is that 10 meters per second squared in a downward direction. So this one needs to change by 10 if you plot the speed. So at 0, we have 15 up. And since the acceleration is down, we would be slowing down. And so we would be going 5 up after 1 second, and now we would be going 5 down, or maybe I should just put a plus 5 down, or anyways, it's negative 5, however you want to look at it, negative 5. Okay, if I put negative 5 and down, it almost sounds like I cancel each other out. So it's a negative 5, or it's a 5 down, 5 down, and so that's the 29. And so not a whole lot there. You could also do a math equation, but I think just counting it out is probably the easiest one. There's nothing to count here. No, it's only counting by tens there. Whereas then 30 is a little bit harder. In fact, quite a bit harder, because it says, now use this information from problem number 29. How far is the golf ball from its starting point? So one thing we hopefully learned in this projectile chapter is we can treat the horizontal and verticals independent of each other. In fact, that was part in the multiple choice. There was one that the correct answer was all of the above, and one of them, I think part C of that multiple choice, said you can treat them independently. And so let's do that. So if I go distance equals to average speed multiplied by time for both cases, let's see what I get. So for horizontal, it's always going 35, 35, 35, 35, 35, 35. You could write this, if you want, as 35 starting, 35 finishing, and divide by 2 for 2 seconds. But I think that's just a waste of ink or pencil lead, because obviously the average is 35. So you average 35 meters per second. For 2 seconds, you're going to get 70 meters. So the golf ball is 70 meters horizontally downrange. Or maybe we'll do it this way, downrange, horizontal. Now, vertically is a little bit harder here because we started with a speed of 15 upwards. I'll call that positive. And then we finished with a negative 5 for 2 seconds. So 15 plus a negative 5 is 10. Divide that in half is 5. So we only have an average upward speed of 5. That's because it started to go down. So it only averaged a 15, even though it started up. Okay. But its average is overall up, so it's still going up. Anyways, for 2 seconds. And so it's 10 meters up. Now, there is another big and important step here. So we are 70 meters downrange, and we are 10 meters up. And it started to go down. So it went up and started to go down. So that would be the path. Now, we're not asked for the distance of that path, which is probably a good thing, because that is the length of a curve, the length of a parabola. And if you guys know some calculus, well, then you can solve that. But we're not going to try to solve it this class. We'll wait for Physics 121 for that. We just want to know the distance away, not the distance it traveled. So we know that it's 70 meters downrange, and then 10 meters up. And so to get what I'll call c squared is then equal to 70 squared plus 10 squared. And so c equals, so grabbing my calculator, 70 squared plus 10 squared, and taking the square root is, let's call it 71 meters. So well, it makes sense. It's not very high, so the distance along this straight line is only a hair more than the horizontal length. So about 71 meters. Yeah, maybe I should circle that. So there's 29 and 30, and like I said, those kind of go together. Now, I'd call 31 kind of a standalone one. It's not grouped with anything, but also 32. So I'll just put it on the same page, but I won't do them together because they're just very different problems. Because 31 is still from our chapter 4, where we've got something, in this case, going in a circle or motion in space. And this has a 165-gram drone that is turning with a speed of, the turn is part of a circle radius of what is the centripetal force. And so in this, we were given this equation, even said that it takes a little calculus to derive that equation. So those of you moving on, I will promise to work this out in Physics 121, where we can apply some calculus here. It's both some geometry and some calculus. We'll call some limits. But anyways, we can come up with this equation. So, and for this class, we didn't prove that equation, but did ask you to use it and understand it. And so that's the force inward. That's why it's called centripetal and not outward, centrifugal. So it's centripetal force. And now we can just put in our numbers. Now, of course, it doesn't say what units to use, but normally forces are done in newtons, and newtons has kilograms in them. So let me really jump back to chapter 1 and say, let me take this 165 grams and convert it into kilograms. So then when I take the speed of 8 meters per second and I square it and then divide it by a radius of 12 meters, you'll see that I will get then a kilogram. Now this meters squared, one of the meters will go away, so this will be a kilogram meter over a second squared, which is a newton. So I'll just put a newton right there for the units. Then I can grab my calculator and go 0.165 times 8 squared and then divide by 12. And it looks like 0.88, and I'll put a 0.88 so it stands out. And 0.88 newtons then is the centripetal force. Now, 32 is the gravitational force. And so here's the universal law of gravity. And it says, what is the gravitational force between the sun and the planet Mercury? So we'll need to know the masses of both the sun and the Mercury and the distance between them, and those are given here. So G is the 6.67 times 10 to the negative 11. The units are Newton meters squared over kilograms squared. It is important to pay attention to this unit so that we make sure that we match, and our mass needs to be then in kilograms, and both of these are given in kilograms, so no real issue there. 1.99 times 10 to the 30 kilograms for the mass of the sun, and the mass of Mercury, 1.90 times 10 to the 27 kilograms. So again, kilograms would cancel off. And then likewise, in the bottom, we need to know a distance between them, and we'll need that in meters. And so here we are going to have to do a little bit of unit conversion because the distance here is 5.79 times 10 to the 13 meters. See, this is kilometers. And I'll square that. Oh, well, I guess it's just meters. And then when that meter gets squared, it'll cancel with that, and you're left with a force in newtons. Okay, so now grabbing my calculator here, 6.67 times 10 to the negative 11 times 1.99 times 10 to the 30th times 1.9 times 10 to the 27. That is a 27. Let me just check that. Is that right? 27, yeah. Then divide by 5.79 times 10 to the 13 squared. And this is then 7.52 times 10 to the 19 newtons. Yay! All right, well, finally, we can get to our last two, which is our chapter 6 and our momentum and an important conservational, and the first of our conservational principles. And I think these go together here. Here's our two objects. We've got asteroid 1, a 7.7 asteroid traveling with a speed of, and it's towards a bigger asteroid. And so maybe I'll just put the 7.7 asteroid going to the right and the 8.8 kilogram asteroid going to the left. It says the 7.7 kilogram asteroid is traveling with a speed of 70 meters per second. And the other one is, let's see, the bigger asteroid is traveling towards the smaller one, that's why the left, with a speed of 60. Okay. And so if you're kind of watching this collision, and I kept the speeds kind of on the low side so they don't shatter into a zillion pieces. I mean, real asteroids are traveling much faster than that, and they hit and they become a bunch of little pieces. But these are just going to kind of stick together here. It says if the two asteroids hit and stick together, what is the speed and direction of the two combined asteroids? So maybe I'll put a little here and go, okay, now we've got smashed together. Now, smashed together, I can think of it as one object where I add them together. So 7.7 plus 8.8, we're looking at a 16.5 kilogram blob. And, of course, remember from the discussion, it will go whichever direction has the most momentum. But it's probably better just to see that if you make that little chart we talked about. Here is the momentum before, and here is the momentum after. So here I would take the mass, 7.7 kilograms times a speed of 70 meters per second, and add it to the 8.8 with a speed of negative 60 meters per second. And that's got to equal. Well, let me just see what that comes out to be. So 7.7 times 70. And let me just put a minus 8.8 times 60. And this comes out to be an 11. And the units are kilogram meter per second. So notice it's a positive number of 11. So that means this has a little more momentum. The first one, the lighter one going to the right, has a little more momentum than the larger one going to the left. So the whole thing has to have momentum to the right. And if you only have one object, it's got to be going to the right. And so as far as the distance go, I'll say right. Right might be a bad word because it depends on how you draw your picture. So maybe I should say in direction of smaller. How would I do that? Asteroid. Okay, so whatever you did in your thinking, whatever the direction of the smaller, faster one is, it would be the direction of the resulting one. And again, you can see that in the numbers because we're going to get a positive number for the speed, which in my picture would mean to the right, because I would put then the mass, which would be 16.5 times the final speed. And so maybe I can squeeze it right in here. So final speed would be then that 11 divided by 16.5. And maybe I'll put it on this side. 2/3 meters per second. So they almost had the same amount of momentum. You can see a bigger one, slower speed, smaller one, faster speed. Not much, they almost balance each other. But this one has a little bit more momentum, so they come together and then barely move to the right. The two momentums were the same in magnitude and opposite direction. The total would be 0, and they would have just come and stopped. But this one over here, the lighter one, has just a little bit more and heads off in that direction. All right, well, I hope I saved myself enough room for number 34 to finish up on this page. But on this one here, we've got a 0.75 kilogram rubber ball is then thrown at a stationary cart. And so we've got this momentum thing going on again. So the momentum before must equal the momentum after. All right. Now, if I take this rubber ball to be thrown to the right, I could say I've got my 0.75 rubber ball thrown at a stationary cart. The rubber ball hits the cart with a speed of 14. So that's the initial momentum of the rubber ball. And the cart is 2.5 times 0. So there's my initial momentum. And again, maybe I'll just get my calculator out, get a number here, 0.75 times 14, and we're looking at 10.5, and the units would be kilogram meter per second. So that's the momentum before the collision, which of course it's all from the rubber ball. The cart's not moving. But then it bounces off the cart and travels back to the thrower at a speed of 5. Okay, so this would be 0.75, and since it's traveling in the other direction, be a negative 5. Now, this would make the cart move, so the cart would be 2.5 times some unknown speed, and that's the question. What is the speed of the cart after the rubber ball bounces off? All right, so 0.75 times this negative 5 is a negative 3.75 and 2.5 v. And so now I can solve for v, because if I take this 10.5 and I move this over, so I'm adding 3.75, I get 14.25. And if I divide it by 2.5, I would get a speed of 7.5 meters per second. And so that's the final speed here. And maybe just to double check that, let's see, 0.75 times a negative 5, add to that 2.5 times that speed of 5.7 gives me a total momentum of 10.5. Yeah, and that's what we had before the collision. We had 10.5, and so we have 10.5 after. So obviously, if the ball goes backwards, the cart's got to go that way in order to keep the momentum in the positive direction. All right, well, there it is, and I hope you did well on the free response as well as the multiple choice. Take care.